Today is our fifth KCS talk for this semester. And the speaker for today is Nusrat and Munia. Okay. The title of her talk is Generative Dermatology AI for Diagnostic Bias Mitigation. Okay. She will present three things. Okay. Two models and the implementation technique. Okay. Let's welcome Nusrat for her talk.
Hello everyone, my name is Nusrat Munia and I'm a second year PhD student here. So I'm working with...
Try again.
Hello everyone, can you hear me?
Is it loud enough?
Hello? Okay.
Maybe a little bit
My name is Nusrat Munia. I'm a second year PhD student here. I'm working with Dr. Imran. Today I'll talk about generative dermatology AI for diagnostic bias mitigation. So here, based on my work on generative AI, I have proposed three models. Two of my models have been published and another one is under review. Today I'll talk about all these three models. And this is the first model, which we call DermDiff, generative diffusion model for mitigating racial biases in dermatology diagnosis. This paper was published last year and I have presented this paper at MICA ADSMI workshop. So to begin with, skin cancer is one of the most common cancer, not only in USA but also worldwide. More than 2 people die of skin cancer in US every hour. So melanoma is one kind of a malignant skin cancer, and statistics has shown that early detection of melanoma has a 5-year of survival rate. So thanks to the advancement of AI and ML, skin cancer can be diagnosed by algorithmically, and it can learn disease-specific features and predict the malignancy from our dermoscopic images like this, and it will predict the skin cancer if it's a benign or malignant case. But the problem is, recent research has found that these models show biased performance towards some subgroup population with sensitive attributes such as skin tone, age, gender, etc. So this is a major concern in healthcare and it goes against the principles of bioethics. So one of the major reasons behind this bias is the training dataset does not contain as many as samples from the minor attributes as the major attributes. So if we compare the skin tones, there is no much samples for darker skin tones compared to the lighter skin tone. So based on Fitzpatrick skin tone level, we define 3 different types of skin tone type A, B, and C. A is the lighter skin tone, B is the brown skin tone, and C is the darker skin tone. Here are some samples for Fitzpatrick dataset, which are sampled for skin tone type A, lighter skin tone type B, brown skin tone, and C is the darker skin tone. So in this work, we focus on 3 problems in dermatology diagnosis. First of all, there is no automated tool for skin tone detection for dermatology. And second of all, there is not enough data samples for darker skin tones, and conventional augmentation methods do not focus on darker skin tones. Here, if you see the dataset distribution of ISIC data, which is publicly available dermatology dataset, it is the largest dermatology dataset publicly available. And here you can see the data distribution of lighter skin tone, brown skin tone, and darker skin tone. And compared to the lighter skin tone, there is only few samples of darker skin tones. Here are some sample images from ISIC dataset. So we propose in DermDiff architecture, we propose 3 architectures. First, we propose automated skin tone detection model, which will detect skin tone type A, B, or C from our dermoscopic dermoscopic image. Second, we propose a generative model to synthesize specific dermoscopic images. And lastly, we propose a fair skin disease diagnosis model to predict skin disease, like if it's a benign or malignant case. So our diffusion model is a unit-based latent diffusion model. So DermDiff is a generative model that is a denoising diffusion process which has a forward process and a reverse process. The forward process gradually adds Gaussian noise to a dermoscopic image until it turns into a totally distorted noise. So it's a simple process. It does not require any training. It can statistically convert any image into a noise. The main thing is the reverse process here is where the model learns to gradually remove noise from an image and generates a new dermoscopic image. So this is the two process of diffusion. Our main target is to train the reverse process to generate new dermoscopic samples. This is the unit-based latent diffusion model architecture. So it's a conditional text-to-image diffusion model. So it takes text prompt as a condition. So to generate text prompt, we use the metadata of dermoscopic images. So here we have metadata information, disease, skin tone type, age, and gender. But for text generation, text prompt generation, we initially use only two attributes, skin disease type, benign or malignant, and skin tone, and generate a generic caption for each of the images in the dataset, like this benign skin disease on brown skin tone for brown skin tones. If it's a darker skin tone, we say dark skin tones. Then pass it to the text encoder to get text embedding for the prompt, and then that text embedding goes to the unit architecture. This unit architecture takes that condition from the text embedder, and then it gradually removes noise from the image and converts into a dermoscopic image. Finally, a VAE decoder is used to convert the latent embedding of the image into a pixel embedding and generates new dermoscopic synthetic image. So we train this DermDiff generative model with Fitzpatrick dataset and then generated sample images. Here you can see some samples generated by DermDiff. These are the benign samples and these are the malignant samples, and you can see the real samples from the Fitzpatrick dataset. And from all the images, the first row represents the skin tone type A, which is the lightest skin tone. The second row is the skin tone type B, which is brown skin tone type, and the third row is darker skin tone. And if you see the generated samples clearly, you can differentiate the skin tone types for 3 rows. Then to evaluate our model, we calculate FID and MSSIN score. FID score represents the fidelity of the model. So each calculates the distance between the real data distribution and the generated data distribution. So lower the FID score means better the generated image quality. And the MSSIN score is the similarity between the generated images. So if the similarity is lower, it means the generated images are more diverse. So we have generated total 60,000 images using the DermDiff model, and among them it had 30,000 benign samples and 30,000 malignant samples. We compared, to calculate FID, we compared it with both Fitzpatrick and Isaac dataset, and when compared with the Fitzpatrick, it provided the lower FID score because it was trained on Fitzpatrick dataset. And if you see the results here, the malignant samples were more diverse and it has lower FID scores. So finally, after generating synthetic images, we build a classification model for downstream classification. It has a simple ResNext based architecture followed by fully connected layer and classification head. It will predict disease status, benign or malignant, and skin tone type A, B, or C. So we train this model with real Isaac dataset, then train with real Fitzpatrick dataset, and then finally we train with real and synthetic images generated by DermDiff. Now we will see the results. So after training that model, we test on DDI dataset. DDI is more balanced dataset. It had all different types of skin tones. It's balanced. And if you see the results for accuracy, F1 score and AUC score across all the skin tone types A, B, C, the model that was trained with real and synthetic images improves all the classification results. Here, especially AUC and F1 score. And if you see the results for darker skin tone, which is C, it improved better AUC and F1 scores. And these are the AUC ROC curve for these three models. Left one is the results from the model trained with Fitzpatrick dataset. Middle one is the results that was trained with Isaac dataset. And the last one is the results from the model that was trained with both real and synthetic images, and it has better AUC scores. So this is the findings from our first paper, first model. Now I will talk about my second model, DermDiT. It's titled Prompting Medical Vision Language Models to Mitigate Diagnosis Bias by Generating Realistic Dermoscopic Images. So this paper I will be presenting at ESB conference next month. So in this proposed DermDiT architecture, we have vision language model based prompt generator, diffusion transformer based text to image conditional generative model, and a skin disease diagnosis model. So the vision language model based prompt generator, if you see some samples from Isaac dataset, it has these dermoscopic images and metadata as gender, disease type, and skin tone. We use vision language model to generate a prompt from this image and metadata. So we construct an instruction to provide it to the VLM. So the instruction contains all the metadata information, and we provide the instructions such as that the generated caption will have all the metadata information, and it will generate a prompt containing all the information from the image. So you can see some sample prompts generated by LavaMed. So LavaMed is a vision language model specialized for medical data. So it was trained only with the medical data. That's why we utilized this vision language model to generate prompt from the dermoscopic images and its corresponding metadata. So after generating the text prompts from dermoscopic images and its corresponding metadata, we train our diffusion model. Here we have used transformer-based diffusion model. It has a couple of components. The VAE encoder decoder. The VAE encoder converts a dermoscopic image from pixel space to latent space where the diffusion process takes place. So basically it converts image from higher dimension to lower dimension for the sake of complexity of the diffusion process. So, and the next one, it has a text encoder. So the text encoder takes the prompt generated by vision language model and converts into text embedding. Similar we have seen in the previous model. And here the forward process converts the latent from the converted image, and then it converts the image into a noise, gradually adding the Gaussian noise. So this is the forward process, and the reverse process, it uses DIT block. So this transformer block is used for the reverse process to remove noise and generate new dermoscopic image. So this DIT block has multi-head cross attention, and which uses this embedding from the text encoder so that the image will have the information from the text embedding, and it will generate corresponding image. So after generating this latent embedding, it will go through another VAE decoder to convert it back from the latent dimension to the pixel space. Yeah. I didn't understand.
When you compare two images, which weight is more important? The difference on the pattern or difference on the pixel values?
So depending on the attributes, so each image has its corresponding attributes here. So based on these attributes, these images can be benign or malignant, or skin tone could be lighter or darker.
Or put it this way: when you train this model here, you have many data sets, right? And when you compare two data sets, okay, there are patterns on this one and on this one. How do you tell that those two patterns are similar?
The data sets from the patterns of different data sets?
Yeah, you have two images. You compare these two images. This one has a pattern, that one has a pattern. How do you tell that these two patterns are similar? You look at the difference on the pixel values or something else.
So if you're talking about the evaluation from the real data and the synthetic image comparison, I guess, so that's how we have calculated the FID scores and MSSIM score. So what it does, it calculates a distribution for real data set, like calculates average and mean for the real data set, and also calculates distribution for generated samples. So then it calculates the distance between two distributions. If the distance is lower, that means the generated samples are more similar to the original samples. Yeah, I have that in my next slides. So this is my DermDiT architecture to generate new dermoscopic images based on the text prompts generated by vision language model. So during inference, that was the training process. During inference, we want to generate more dermoscopic images. So for doing that, we need to generate a text prompt that will have the metadata information. Like if we want to generate a benign skin disease dermoscopic image with a lighter skin tone, it will have those attributes in the text, and it will be passed to the text encoder to get text embedding, and then it will pass to the this DIT block, and then the diffusion process will start from the latent of noise, and then convert it to a less noisy image based on the condition of the text embedding. So it gradually removes the noise, and finally the VAE decoder will convert it back to the pixel space from the latent space. So we will have new dermoscopic images based on the text prompt.
So what is considered noise here?
So this is the diffusion process. So what the diffusion process does, it has two processes, forward process and the reverse process. The forward process is just converts image to noise, and the reverse process is takes a random noise like a Gaussian distribution, and from that Gaussian distribution, it will gradually convert it, and then it will generate a new dermoscopic image. So to generate a new image, so it starts from the noise. it starts from a noise embedding and then convert it latent embedding.
All right,
Do
go
you have
ahead.
any other question?
Well, I'll ask you a question at the end.
Okay. So that's the part of diffusion process where you convert the noise into a dermoscopic image. So during this process, we utilize the transformer-based DIT block that learns the parameter to remove noise and finally converts into an image based on the condition passed to the text encoder. And then we generate samples using this DermDiT. And we have 5 different versions of our DermDiT model. We have used both unit-based latent diffusion model and transformer-based DIT model. Initially, we trained this model without passing any condition, so it learns the distribution of dataset and generates randomly new images. So this is the unconditional diffusion model of using both latent diffusion model, which is unit-based, and the transformer-based DIT model. And then I have used 2 attributes from the image metadata. First one was skin disease status, benign or malignant, and second attribute was skin tone type A, B, or C. And for VLM, I have used the lava model to generate text prompt and then train both LDM and diffusion transformer model and generated prompt, generated new synthetic images. And finally, I have used 5 attributes and used the lava-made vision language model and trained the DIT model and generated new samples. So to calculate, we have calculated FID. The FID measures the distance between the real and the synthetic data distribution. So generally, FID is calculated based on the pre-trained inception model that was pre-trained on the inception dataset. But for this case, we have fine-tuned this inception V3 model on dermoscopic images to get better representation of the dermoscopic images. So here I have shown FID both on the pre-trained inception model and the fine-tuned inception model, and then we also show the MSSIM scores. So if you see the last model that was trained with the captions generated by lava-made model and trained with diffusion transformer has the lowest FID and MSSIM score, which represents, yes?
Finish your sentence.
Yeah. So the last model performs better than other models.
So my question was, why did you use 2 different VLMs? The lava and the lava-med.
The lava model is trained with natural images and paired with natural data, but the lava-med is specialized for medical imaging.
So you've got 2 different, possibly independent variables, 2 attributes versus 5 attributes, lava versus lava-med.
Yeah.
Did you also look at, let's say, 2 attributes in lava-med or 5 attributes in lava?
So I don't have those results, but we utilize lava-med and see how it works on 5 attributes.
Okay, thank you.
So these are my 5 models. Unit-based latent diffusion model and transformer-based diffusion transformer model DIT. So here I show some visual images from the samples generated by DermDiT and the real ISIC. Here is the real dataset from the ISIC, and here are the unconditional models, LDM and the DIT, and this is the LDM condition on 2 attributes, and this one is DIT conditional on 2 attributes, and the last one is DIT conditional on 5 attributes. So if you see this DIT-based model, conditional models, these samples are more similar to the Isaac real data samples. So here comes the pixel-wise evaluation that you have mentioned. So I have calculated the kernel density plot here to compare the kernel density between real and synthetic images. The first row is the comparison of kernel density plots of the real and synthetic of these 5 models. So if you see these two, the overlapping of real data density and synthetic data density quite overlaps with each other. That means the generated images are quite similar to the real images. And the second row is the principal component of real and synthetic images. So if you see the last two, the distribution of real and the distribution of synthetic images quite overlaps with each other, which represents the quality of genetic images are quite similar to the real images of the dermoscopic images, Isaac dataset. So after generating synthetic images, we evaluate the downstream diagnosis task. So we classify the disease status, benign or malignant. So we train with real Isaac dataset, and then we train with synthetic dataset. And finally, we test on these 3 datasets, DDI, Isaac, and Fitzpatrick. Isaac is in distribution dataset, test dataset, and the other 2, DDI and Fitzpatrick, is out distribution test dataset. So that's why Isaac has better AUC and recall scores compared to other models, other data. So if you see the recall and F1 scores of real and synthetic, synthetic images improve the results of recall and F1 scores, which means that the model trained with synthetic images has more class balanced accuracy and recall scores compared to the model that was trained with only real Isaac images.
When are those factors like color of the skin removed before you establish your pattern? But if you go back to the previous slide, the next one. No, for those patterns, okay.
Yeah.
No, the color of the skin factor, of course, has already been removed, right? Because if you have a darker skinned guy with a light skinned guy, how do you tell that their patterns? This is the pattern for dark skinned guy, or that's the pattern for the light skinned guy. Those factors have to be removed first, right?
No, we didn't compare individually for darker and the lighter skin tone. We
compare people with the same skin color.
No, these are the real data set. So the real data set has all the images from all the skin tone types.
Then my question, when are those minor factors removed before you compare their patterns?
No, we have those patterns in the real data set. So it's just comparing if those patterns exist in the synthetic images or not.
You could have patients with darker skin or light skin. How do you compare their patterns? Darker skin guys, pattern probably is very difficult to identify.
Perhaps we can move on for the moment and save questions for later.
So this is the evaluation of downstream diagnosis with classification of disease status, benign or malignant. So it improved the Using the synthetic images, it improved the recall and F1 scores for all the test data sets. And this is my third model, which is still under review. It's integrating classification model on conditional diffusion model for improving fairness in deep learning-based skin lesion classification. So here we propose classification model integrated with the conditional diffusion model. So it has integrated disease classification model with the diffusion process. The diffusion model here is class level condition instead of text. So it takes class label such as if the class label is benign or malignant, and then based on that class label it will generate corresponding dermoscopic images. So here we simultaneously train both classification model and diffusion model and update the diffusion loss incorporating the classification loss. So here you can see the classification model here and the diffusion model here, and it has two hyperparameters. First one is here, gamma. The gamma hyperparameter controls the input to the classification model. So based on the value of gamma, it either takes input from the real image, or it takes input from the generated image from the diffusion model. So the idea behind is if the classification results of a generated image fails to classify the image, then the classification loss will be added to the diffusion loss, and that way the model will be able to learn to generate more specific class specific generation of the diffusion model. So the lambda here is the hyperparameter which is classification loss weights. So classification loss is weighted with lambda and then added to the diffusion loss. So based on these two hyperparameters, we have 5 different settings, and the setting 1 is just training the diffusion model without integrating any kind of classification model, just the normal diffusion process. And as you know, diffusion model has lots of parameters compared to the classification model. So the diffusion model will take more time to train compared to the classification model. To incorporate that, we come up with different settings. So in setting 2, we train the classification model for integrated classification model on the last 2 epochs of the diffusion training with gamma 0.25 and lambda 0.2. And in setting 3, we start with the value of gamma 0 and periodically increase the value of gamma. So gamma value 0 means it will always take the input from this real data real data embedding, and then when it increases the value, it will randomly take, based on the value of gamma, it will also take the input embedding from the generated image. Because initially the classification model needs to learn some feature embedding for the real images, and initially the diffusion model won't be able to generate good images. So not to confuse the classification model, initially we put the gamma value to 0. And then for updating the classification weights, we only update the classification weight only once in 3 steps of diffusion process, and this is the setting 3. And setting 4 is similar to setting 3, but in this case we update the classification parameters each step of diffusion process. And in setting 5, which is also similar to setting 3, but here the value of lambda instead of 0.2, we use the value 0.3. This is the 5 settings of our proposed model. And then we train this 5 proposed model with the Isaac datasets, and we visualize those images. These are the real Isaac images, and these are the generated samples from setting 1, setting 2, setting 3, 4, and 5. It's hard to differentiate those images. So I'll go to the quantitative analysis, which is FID scores. So if you see the FID scores that did without any classification model and did with classification model, FID scores dropped way too much. So when we induced the classification model with the DIT model, so it was able to learn more specific features, and it was able to generate images that learns classification and disease attributes, and it helps the diffusion model to generate more feature realistic images. So here we show FID scores based on 5K samples, 10K samples, and 20K samples, and we also show the MSSIM scores. Here in setting 2 and setting 3 and setting 4 provides better FID scores compared to other models. And then here we compare classification model for downstream diagnosis. The classification model in setting 1, this classification model was trained independently only with the real Isaac dataset. And here these 2 and 3, these models was trained during the diffusion process training. So when it was trained independently with the real Isaac dataset, it didn't see any synthetic images. But these 2 settings, it was trained with both real, and it has seen the synthetic images during its training process. So if you see all the results, the classification models in setting 1 and in setting 2 and setting 3, comparatively they provided similar results, which indicates that the diffusion process really learns the distribution of real image dataset, which enables the classification model to generate more similar results that was trained with the real Isaac dataset. No. So this is the diagnosis results, which classifies dermoscopic images if it's benign or malignant cases. So, so if I conclude my works today, the diffusion model can improve the fairness by generating realistic synthetic images, and by using the large vision language model, it can improve the quality of synthetic images. Also, integrating the classification module improves the quality of the synthetic images, and these synthetic images can improve downstream task performance for any subgroups. And in future, we plan to do a more extensive evaluation on segmentation tasks too, and we also plan to evaluate these synthetic images by dermatologists. So if you have any question, you can ask.
Hey, it was a nice presentation, and you did solve, like, one of the main problems here is the data imbalance thing. There was not like more data, so you generated new data and you have trained on it. So you have also compared the distribution. That's okay, but this might have introduced a new kind of problem, like although the distribution is quite similar with the lava and the lava med, so yeah, this one, although the distributions are similar, did you get each and every generated image checked by any like licensed clinicians or like medical doctors?
No, I haven't yet, but this is the part of our next plan to check those synthetic images by any dermatologist or any specialist.
Yeah. Okay, that's good. And the second question I have is, um, the images that you have used, are they under specific lighting conditions, or they are just under natural light?
They are just natural lights.
Just natural light. So you don't have data, or neither do you have data, nor you did generate data in lights outside, like visible range, like infrared and stuffs like that. Because I do think if you use infrared, sometimes these kind of lesions might become highly contrastable to the skins, irrespective of the skin's color. I don't know, I'm just asking, like, does your dataset also include some images under infrared, or is it all under natural light?
No, it's just all under natural light. So, but it's a new way of thinking. Or we can think about that too.
Yeah, because sometimes this kind of lesions fluoresces in different spectrum of electromagnetic waves, so you might want to look at that. But other than that, it was a great presentation, and you did try to solve these issues. Yeah, it's nice. Thank you. That's all.
Another question right here.
Thank you for your presentation. So my first question is about the metrics you evaluated, in particular the FID metric. So how many synthetic images and how many real images you used to evaluate these scores on? Because normally some of the metrics are dependent on the number of images. The more images you have, the better characterization of the distribution you capture, and this results in reduced FID. So yes.
Yeah, to calculate FID, I kept the number of samples in generated and real images similar, and most of the cases I used almost 30,000 synthetic images and also put 30,000 in real images, so, and then compared the two distribution to calculate the FID.
Right. And secondly, did you say that in your future work you plan to incorporate like label generation and involve medical experts in labeling the synthetic images?
Yeah.
Okay, thank you. That seems like natural extension to your work.
Questions? We still have, time, actually plenty of time for questions.
Thank you for the presentation. I had a little abstract question. Is in the first project you do diffusion to generate the malignant photos, and in the second one you have text prompt added to it. So, what are exactly the benefits of doing so? I know you explained it, but why do you want to use the text to get specific samples of specific disease, or does it have more benefits than that?
So if we include more attributes, it will have like more information on the specific image. So if we provide more information, it will help the diffusion process to incorporate all the information and generate more realistic images.
Okay.
That was the point.
Okay, so if you use the text input as as added input, does it lead to better distribution to the real data set compared to the just generating without the text input?
Yeah, that thing I am also running some experiments on that. So I don't have the results, but the intention is that including more attributes will end up with better results in the diffusion process.
Perfect. Yeah, I'm doing some research related to this. So thank you. Yeah.
So you're doing similar research or
Using the same tools but different domain. Yeah.
So my question is, are those tools developed by you or developed by somebody else?
The diffusion process is not developed by me. The diffusion process is developed like 2 or 3, 4 or 5 years ago. So I'm using the diffusion process and training on dermoscopic images to generate more dermoscopic images. But because the current diffusion models, they are not trained on any medical images, but they are trained on natural images. So if you have heard about the text-to-image models like some online text-to-image tools that if you provide caption, it will generate new AI images. So those are the models, those kind of models are trained with natural images, but here it's only dermoscopic image based, it will only generate dermoscopic images.
So is there a fair description that this work here is only the training process, using tools to develop the training process?
Mm-hmm.
Another question is a set of 30 images big enough to have a general the result will be considered general enough.
I didn't understand. Sorry.
Well, you in most of cases you use 30 sets of images to do the training,
30,000,
right?
yeah, 30,000.
Is 30,000 images considered a domain big enough?
Yeah, to calculate the FID score, it is like better to have more than 10,000 images. So in general, 30,000 is a good sample for calculating the FID score.
Yeah, but I don't think that those data sets represent most of the possible cases. You don't have darker skins showing in your data set. Most of the cases seem to be a very specific group.
Yeah. These are the type of dermoscopic images. So each of the images have like this skin image and including the part of the skin where it was affected.
Questions?
Hello. Okay. So thank you for your presentation. So I just had a question in the last part, I guess, in the settings, right?
Mm-hmm.
So I found that so you have done like 5 settings, right? So in the bottom 4, you have kept lambda to be 0.2, 0.3, and so my natural question was that why did you select these numbers, and like you stopped at 0.3, right? So basically, like what's the mindset or what's their thinking about that, right?
So yeah, these are hyperparameter. We can experiment with more values of lambda and gamma. So we try to keep it like less because this value is the weight for classification loss. So here this value is weight value. So it was like multiplied with the classification value, then added with the diffusion loss, because diffusion loss is like our first priority, then the classification loss. So we try to keep it like less than 0.5.
Okay, so can you just take the slide to the result of that, right? Maybe after that, yeah, at this one, right? So just looking at these results, I see that these have different kind of. Okay, so sorry, different kind of values for. Oh, sorry. So for the bottom 5 settings, for the values for FIDs and the MSSM are quite different for the 4 settings, right? So I'm just like asking the question, right? What if we increase the value of lambda, or what if we put some value between, let's say, 0.2 and 0.3? Because for FID, setting 4 has like the lowest for the FID 5K and 10K, but in the same case, FID 20K for that setting 3, and then MSSM that's setting 5, right? So like my general question is that how did you conclude? What is your conclusion in that?
So the idea is how the classification model is improving the diffusion process or not. The comparison is that with the DIT model with classification and DIT model without classification. And for those gamma and lambda, we can experiment with any number of value, and we can experiment more values, and we can come up with optimized value of gamma and lambda to get more better FID and MSSM score.
Yeah, also I get it now. Thank you so much.
Well, I think that, yeah, he raised the important question, the lighting condition.
Sorry. Yeah, I did have another question. I don't have much knowledge in this area, but in the first paper when you mentioned about the classification for the skin tones, is it a standard metric to have 3 skin tones, or is it just a non-standard thing where you make like the 3 skin tones? Does it have a like standard reference of what skin tones is what intensity? Because I can make a darker skin tone, make lighter by like imaging it under white light. I don't know, like brighter light. So, like, do you have like these 3 are the known skin tones, or is there a scale for skin tones?
Yeah, I have used the Fitzpatrick skin tone.
Can you speak louder?
Okay.
Oh, got it. So Fitzpatrick is a metric for skin tones?
Yeah.
Oh,
So
got it. Yeah.
yeah, it has 6 labels, 1, 2, 3, 4, 5, 6. For my experiment, instead of taking all 6 classes, I have to like 3 classes. So it's Fitzpatrick 1, 2 is the light, and 3, 4 is brown, and 5, 6 is dark.
So light, brown, and dark is given by your visual analysis, or is it from some reference?
So Fitzpatrick 1 is the lightest skin tone from their definition, and 6 is the darkest skin tone from their definition. So I just like divided.
Interpolated it
Yeah.
equally. Oh, got it, yeah.
Instead of 6, I have like 3 classes.
Got it. That answers my question. Thank you.
Any other questions? You're doing similar work, so you should have questions.
I'm doing just using the tools, but
Just using the tools.
Yeah.
So
All
if you
right.
have any more questions, you can email me, and if you want to know more about my research, and if you want to do any collaboration, you can email me and I can reach out to you.
All right, then let's thank the speaker again for exciting talk, okay?